But I didn't make it formal in that I did not print out, like reprint a changed schedule, but we're skipping section 5.4 just for the sake of time. So we're going to be looking at section 6 or chapter 6 today. We're starting with 6.1. All right, so 6.1 has to do with, again, critical points and stability. It's something that we've talked about before. But here it's not going to be a single equation. It's going to be critical points of a system. So critical points, stability, and what we call the phase plane. We're going to talk about a phase portrait, phase diagram. All right. So, a little motivation. So say we're given, or definitions, terminology, say we're given the system just general. So x prime, for some reason in chapter 6, they start writing it as dx dt. So it's x prime, x1 prime, x2 prime, but dx dt, and say it's given as some function of x and y. Okay, and this notation doesn't matter what the capital F of x, capital F is, it's just some function of x and y, possibly just one. All right, and y prime, again, some function of x and y. Just to distinguish them, they're not the same functions necessarily, so g of x, y. Now, such a system, we've heard the word autonomous. What's an autonomous equation in the context of a single differential equation? Remember what autonomous refers to?
It's only defined in terms of itself. It doesn't have like a, is that what it is?
Right, there was no independent variable.
Yeah, that's it.
Right, so it just involved the expression on the right side or whatever only involved the dependent variable. So if this is a function of x and y, and they're both the dependent variables in this system, t is the independent variable. If I just have expressions involving x and y only, doesn't involve t, then we call it an autonomous system. So it's autonomous if neither of these expressions, neither of the equations in the system involves the independent variable. T. Okay? So autonomous. All right. Now solutions, and we've gone about finding solutions for, first order, right? First order systems with constant coefficients, homogeneous. But solution comes in the form, x, and x is a function of t, and y equals y of t, can be plotted together, and we could think of it like we saw before as a parametric curve. Okay. Parametric curve, sometimes you've seen them like this, x of t, y of t. So each value of t gives you a point, x, y in the plane. So t is called the parameter, and we can think of this, the solutions, if we put them together, right? Originally they came in the system. If we graph them together as both functions of a third variable t, then we have a parametric curve. These are what we call trajectories of the system. Okay, and of course dependent on the initial condition for x and y. So each initial condition will give rise to a specific trajectory of this system. Yeah? Okay, that can be plotted in the xy plane. All right. Now we've talked about the term equilibrium solution or critical point. We also have critical points of the system here. What did they mean before in our original context in terms of a single equation? What was a critical point? where, yeah, dy dx was 0, yeah, or undefined in terms of a function. A critical point is a point in the domain where the derivative is 0, or undefined. In terms of a system, a critical point is going to be a point where not only dx dt is 0, but also dy dt is 0. So a critical point of system is a point, and the book sort of refers to an x star, y star critical point.
It's gotta be the origin if x and y are both 0.
Oh. Well, it depends on what these functions are.
Oh.
Yeah, because it's x prime and y prime, so. It's not-
Oh, right. X prime and y prime are not always x and y. Sometimes the point 0, 0 will be a critical point.
Sure.
So a critical point is a point for which, if I plug in those values, x star and y star, it makes dx dt equal to 0. And those same points make dy dt equal to 0. And that expression is given just by x g of x, y. Okay? So it's a single ordered pair that makes both dx dt 0 and dy dt 0. So it simultaneously makes x prime and y prime equal to 0. Well, if that's the case, if dx dt or x prime is 0 and y prime is 0, then what happens in that system? So if our initial point, for instance, happened to be a critical point, what's that? It wouldn't move. Dx dt is 0, right? So x is neither increasing nor decreasing. Dy dt is 0, so it's neither increasing nor decreasing. So that's, you can call it an equilibrium point. It wouldn't change. If the trajectory hits that, it stays there. All right. I'm going to start on the next page. I don't want to start here. Let's do an example.
Can we run into R3 with these examples? Is this chapter, this section going into R3?
No. It'd be cool if it did, and you could translate it into 3 dimensions. It's just that each example will take half the class. But you know, our method of, and it is going to involve, of course, with a system. It is going to involve the coefficient matrix and finding eigenvalues and things like that. So we're going to use the eigenvalue method to not just find, but to categorize the type of critical point that the system might have, okay? Or critical points. There may be more than one. All right. So let's look at an example of just finding critical points. So find critical point or points, don't want to give it away, there might be multiple, of the system dx dt equals 1 minus y squared. Notice this is not linear. And dy dt equals x plus 2y. All right. So what we're going to be doing now is not necessarily solving the system. In other words, we're not going to necessarily be finding a closed function for x of t or y of t right now, okay? But just finding a critical point or points of the system. All right. So when we do this, we just, well, I want to set that equal to 0. Because the critical points I'm seeking are points, x, y pairs that make dx dt and dy dt equal to 0. So we set those, I'll call that equation 1 and 2 in pink, and they're equal to 0. So notice the top equation only involves one variable, right? So we can solve 1, and what are the solutions going to be?
That's minus 1.
Y equals plus or minus 1. Yeah, y squared has to equal 1. Good. So that expression, yeah, and one of these functions, we call it capital F of xy, g of xy, could involve only one variable. It's just a function potentially of those two variables, x and y. All right, so y equals plus or minus 1. Now, that has to hold in the other equation. So what we can do is let's start, for instance, from y equals 1. If I take y equals 1, plug it into 2, and what's that going to give me? Sub that into equation 2, y equals 1, we get x plus 2 times y equals 0. Right? So what does x have to equal? Mm-hmm.
Oh, we're positive to that.
Oh, well, we're going to take care of these one at a time.
Oh, sorry.
So with y equals 1. Yeah, so over here, I'm just going to make a column of the critical points that we find. So, and the ordered pairs, order, negative 2, 1. Okay, and you can see if you put negative 2, 1 in here, of course, this doesn't depend on x, just put 1 in there, negative 2, 1, you get both of them equal to 0. All right. And depending on the types of functions you have in here for dx, dt, and dy, dt, then you just got like this kind of ad hoc just method, just substituting things until you can solve it. There's not a direct approach, especially if they get more complicated. All right, but y has to be 1 or negative 1. Now, if we take the other one, substitute into 2, then it's x plus 2 times negative 1. That's x minus 2 equals 0, and we get x equals 2. Okay, so our critical point would be 2, negative 1. So we have only two critical points in this system. All right, so one thing to notice, if you happen to choose like if it was an initial value problem, if you had initial conditions, if the initial value, say x naught, y naught, just happens to be a critical point, then neither x nor y can change because dx dt is 0 from then on. dy dt is 0 from then on. X and y are fixed. They're stationary. Okay? So that's why oftentimes these are called equilibrium points or equilibrium state. Okay. All right. So what we can do once we have a system, and notice there are no initial conditions given in our original example, but we can create what's called a phase portrait or phase diagram. And what a phase portrait should show, well, it should show critical points. Along with several trajectories that show the behavior, especially behavior near the trajectories near the critical points. So the behavior of the system, especially near those critical points. Okay. So it's akin to a direction field, okay? But we're talking about trajectories, so there will also be a direction because these are going to be parametric curves. So they could go left to right. They were parametric. They could cross, they could go left and right. So it's going to be a vector field. Vector field also shows direction as well as magnitude, so the speed of the trajectory at any point. The vectors, the magnitudes of the vectors themselves will show the speed. Okay? The speed at which it's being traced out or parameterized. Okay. And what it does is it shows, well, dx dt, dy dt at any given point, right? It calculates both of these and puts them in the plane. Now, what this is called, if I graph dx dt and dy dt, this is our x prime, y prime. And I'm writing vector notation. If you're taking Calc 4 or taking it right now, this is probably more familiar, but column vector of x prime, y prime. Okay, so it's a vector field, and it shows, basically, these are the tangent vectors to that trajectory. It's a G, not a J. Tangent vectors. All right. So section 6.1 is very visual. It would be hard to categorize everything by just verbally. So, according to my calculations, this thing works. Try it every once in a while. Once a minute. Should reload.
Allow.
I think it all allow.
Where is it?
Upper right hand corner.
Oh, okay. That's what that was. Allow now. Okay. There we go.
Nice.
Okay, so this is the same thing, P-plane, D field and P-plane. Now we're on the second part of it from Rice University. Pops up the same looking things. Except the big difference is that it's not a single differential equation that you enter in here, it's a system. Yeah? Okay. So let's put in the ones I had, this example, 1 minus y squared. And dy dt was x plus 2y. All right, and I'm going to go from -4 to 4 in both directions. Get phase plane. All right, there it is. All right, so another distinction between this and the D field, direction field. Direction fields, yeah, they show the line segments that represented the slope of the curve at any point. But they didn't have a direction associated with it because it was a function of, you know, the independent variable x or whatever, so it always goes one way, we got a function. Here, they're represented by, these are actually vectors. So they show the direction as well, and notice, not all the magnitudes of these vectors are the same. So right here, it's real short, right? And that meant that tells you that dx, dt, dy, dt are not very large. The magnitude of that tangent vector, very small, right? So when dx, dt, and dy, dt are 0, that gives us the 0 vector. It would just be a point with no direction, no magnitude. That would be a critical point. So it's very hard to see them here because you can sort of search for where the magnitude is smallest, you know, where on here are the magnitudes near 0. And it looks like over in this region, very tiny tangent vectors. All right, the other thing that's like D field though is that it lets you put in trajectories. So click on an initial condition and it would give you the particular trajectory curve. Okay?
Why is that coming from the critical point?
Oh, that's weird. Yeah. What was one of our critical points was -2, 1?
Yeah, it's -2, 1.
In fact, they all emanate. Look at the vectors around it.
Are they going to or
The
coming?
vectors are pointing away.
Yeah, so why does it trace back towards it?
It doesn't. When because I started right here, so it does fill in like
Oh,
first
okay,
time.
as if it would
Right,
come
right.
from it.
But all the vector quantities are pointing outward from it. Yeah. So this is one of our critical points. It's like a black hole, except it's in reverse. It's not sucking everything in towards it. It's spitting everything out.
Oh, it's a,
It's a
what's that called?
Supernova.
source.
Sorry.
What is was the term we used for it, we're talking about equilibrium solutions, there was the stable,
Oh,
unstable.
unstable.
Unstable. There you go.
Right. So if you'd started near this point, these vectors that represent the tangent vectors shoot you away from it. Right? So yeah, it's unstable. It is an equilibrium point. If my initial point was -2, 1, it would stay there forever. But if I'm a tiny bit away from that initial point, it shoots you away. So yes, it would be an unstable equilibrium. Also, it's called sometimes called a source because everything's radiating out from it, right? If all these vectors were reversed and all trajectories led towards this, it's like an attractor. Then it's a sink. Yeah, then it would be like a black hole. And it's a sink that draws everything in towards it, like a drain, right? All the water goes, circles and goes.
What about the
Curves that are actually traced out on there, that's the actual parametric curve
Yes.
of the system.
So notice this is the x-axis, this is the y-axis. At any point on here corresponds to a particular value of t. So the parameter t is invisible, but it's a parametric function. Yeah.
What about one where it goes away from a source but then heads towards the sink?
Yeah, there's all sorts of stuff. And this is just one type. Yeah, there's different kinds. What was the other one we found here? We had -2, 1, that's right here. And 2, -1, right here. Look at this. Yeah, things are going weird here.
It's a saddle point.
It is. That's exactly what it's called. So some trajectories lead you towards it and then veer away or something like that. You know, if you start on one trajectory, it'll shoot you away. If you started on a different trajectory, it might shoot you towards it. But overall, you could never get there. It's like holding the same side of two batteries together. You know, certainly it's hard to explain. But it is exactly. It's called a saddle point. So there is a trajectory that would lead you to it, but orthogonal to that, the trajectory, if you're on that, would shoot you away from it.
Sure.
Yeah. So this together with some of these trajectory curves, this is a phase, phase plane, phase portrait. That's all. Yeah, you get all kinds of cool stuff.
Yeah, seriously, keep clicking, this is really pretty.
Yeah, it is. It's nice.
Nice.
You guys, here's another reason to play with this because you can make the background
Oh,
big
no,
and
that's
black
right.
or whatever.
That's not.
You gotta turn on
Yeah, I like that.
You gotta
Purple.
Not
Right,
very
yellow.
Yeah, it's not. I don't. Oh, this is.
You gotta do that one in dark.
That's better.
All right.
Stare out of the high definition like that. Server doesn't run Java on my iPad.
Oops.
Yeah,
Why do you need to do that?
All right. Well, this is a prefabricated one. This is the default one that they give us, and it's got some x squared, y squared terms. It's certainly not a linear system. Oh wow. That's something different.
No, what is it?
That's something totally different.
I don't know, but I like it.
I need to know what it is.
I think it's a elliptical one that spirals inward.
No, it's not.
Has to do with anyway. The orbits, yeah, the orbits of a specific trajectory. Anyway, all right. So yeah, we can have unstable and stable equilibrium, and we could also have different types of critical points. We saw one that was a source. That's called a node. And we could have nodes and things like that. In fact, let me pass this out. So instead of going through all the stuff that the book does about how they're characterized and the definitions of them, we're going to do a couple examples, but I'm going to pass out this sheet. And on the back side, we're going to be, it illustrates a few different types of critical points.
May I have one more?
Yeah. Okay. So stability in the phase plane. One of those for myself. All right, so let's do another example. And I want to sort of do some examples that lead to the particular cases that you see on the back. Okay, instead of just showing you the picture and saying, oh, that's what that is, that's what that is, that's what that is. We're going to do a few examples and point out, okay, this leads to that situation that you see. All right, so say we got this system dx dt. Dx dt equals negative x.
Can you switch over to one?
Oh, yes. All right, so dx dt equals negative x. Dy dt equals negative k times y, where k represents a positive, or a non-negative, no, I should say non-zero. Okay, because we're going to look at different cases. So k is not 0, so we can divide by it and all that. Now,
Is it a constant?
yes, constant k, not equal to 0, so I do have something over here that's not constantly 0. Let's write this in matrix form. So x bar is going to represent, or x bar prime, dx dt, dy dt, or x prime, y prime. So we've done some of this. What would that matrix be? Right. Now, I want my coefficients, so I got negative 1x plus 0y. This one could be written as 0x minus ky, or plus negative ky. All right, so my coefficient matrix A would be negative 1, 0, 0, negative k. Okay. All right. Now, how would we solve this system using this matrix form? It would depend on eigenvalues. All right. And sometimes it's helpful, as soon as you do this, write down that matrix A minus lambda I. It would look like in the diagonal, subtract lambda, 0, 0, and negative k minus lambda. All right, because we're going to work with that, so it's better to have it written down. All right, so to find the eigenvalues, we solve the equation, determinant A minus lambda I equals 0. So that has to be a singular matrix. And what do we get? Well, let's actually write it out. We're going to get negative 1 minus lambda. And you know what? I'm going to pull out those negatives. I'm going to factor out the negatives, because when I multiply that diagonal, those negatives are going to cancel. So try and follow with me. I'm going to factor out the negative, and they would cancel. This would be 1 plus lambda times, pull out that negative, k plus lambda, minus 0 equals 0 in this case. Okay, so what are my values for lambda here? So lambda 1, lambda 2, and the other one, lambda will be negative k. Okay. So let's find the corresponding eigenvectors. So let's take the first one, negative 1. All right. So I put lambda equals negative 1 in here, and we solve this equation: A minus lambda I times V, that's the eigenvector we're looking for, equals 0. Okay. So A minus lambda I, what does that look like when lambda is negative 1?
0, 0, 0.
Oh, right.
K plus 1.
0, 0, 0, negative k minus negative 1, that's negative k plus 1. Right. And I'm just going to call the components A and B, and and we get the 0 vector. All right. So notice the first equation, 0a plus 0b equals 0. So that tells us nothing about what a and b are equal to, but the second equation says negative k plus 1 times b equals 0. So what does b have to be?
K negative K plus 1.
0, right? If negative k plus 1 is a constant, times b equals 0. So b would have to be 0.